Hello everyone, I'm Jerry Zhao from Nanjing University. I would like to share our work, Asymmetric Masked Distillation for Pre-Training Small Foundation Models. This is a collaborative work, including the Multimedia Computing Group at Nanjing University and the Shanghai Artificial Intelligence Laboratory. Let's start with the background of the task. Action recognition is specific to a collection of human behaviors, and its task description is that given a video of human activity, the model is required to perform video comprehension and reason about the character behaviors occurring within the video. And then let me introduce you to model distillation. Model distillation is a model compression technique that mimics the behavior of a larger teacher model by training a smaller student model. The goal is to reduce the computational complexity and storage requirements of the model while maintaining performance. Model distillation increases efficiency, reduces resource consumption and lowers costs. This work focuses on feature distillation, which achieves unlabeling by aligning the middle layer feature outputs of the teacher model and the student model. Recent articles on feature distillation are shown here. Let me next describe the purpose of this work. Self-supervised models have shown great potential in computer vision thanks to the pre-training paradigm of masked auto-encoding. This paper aims to pre-training relatively small models in an efficient manner and enhancing the performance in downstream applications. There are certain challenges in distillation of large masked autoencoder pre-trained models, including the computational bottleneck caused by larger teacher model, the information damage from high masking ratio and alignment difficulties due to different feature spaces. The architecture overview is here. The overall framework of AMD is a two-stream distillation structure with a student branch and a teacher branch, and the teacher is a larger MAE pre-trained model. It is worth noting that AMD only works with the encoder of the teacher for distillation, whereas the students were required to accomplish the pixel reconstruction task with a decoder. Feature distillation occurs between the corresponding layers of the student and teacher models, and AMD employs both direct alignment and generation alignment in a serial way to respond to our asymmetric masking strategy. The asymmetry lies in the difference between the inputs of the student and the teacher. After performing the cubic patch embedding, our asymmetric mask strategy is then applied, resulting in the input sequence of the student and the teacher, respectively. The length of the input sequence of the student is shorter than that of the teacher, and the visible token index of the student is a subset of that of the teacher's. And the serial alignment is a feature alignment strategy designed for the asymmetric mask, which combines direct alignment and generation alignment with a shared projection function. The first step of direct alignment is to apply the projection to the student to align the dimension of the teacher. In practice, we employ a linear layer for this purpose. Thus we obtained the student features used for direct alignment. We then serially use these features to continue with the generation feature alignment. This serial alignment can appropriately reduce the difficulty of the generation alignment task. We tested AMD's performance on video tasks and image tasks separately. In the video domain, we performed action recognition experiments on the Something in Something v2 and Kinetics 400 datasets, and the results show that AMD can significantly outperform video MAE for both small and base models. On the AVA dataset we performed action detection experiments, and we were also able to get good performance. In the image domain, we conducted image classification experiments on ImageNet 1K, which can outperform some previous methods. Therefore, AMD performs well in both video comprehension tasks and image recognition tasks. We believe that AMD is a small and robust MAE model. As MAE benefits from more training epochs, we experimented AMD at different training. Compared with the video MAE base model, AMD performs better at a larger interval on different training schedules. It is significant to note that the performance of the teacher model on SSV2 is 74.3%, and our best result at the training schedule of 800 epochs is only 1% lower than it. Therefore, our AMD is a small and strong model thanks to the sufficient distillation. To verify the generalization ability of the distilled pre-trained model, we pre-trained AMD for 800 epochs on K400 and fine-tuned on SSV2, UCF 101 and HMDB 51. Our asymmetric distillation approach significantly improves the generalization ability of video MAE. It is notable that on the SSV2 dataset, the transfer performance is improved by 4.1% compared to video MAE, which indicates that AMD reduces the risk of overfitting in transfer fine-tuning and demonstrates robust transfer performance. Furthermore, we attempted to adjust the masking ratio for the teacher to 0% in AMD's default settings, which resulted in a relatively poor performance. We believe that the extreme setting would make the generation alignment difficult. Specifically, we think that there might be a conflict in our training goals. The conflict becomes more apparent under an extremely low masking ratio of the teacher model. Our training aims to do two things. 1. Reconstructing the image pixels, and 2. Aligning with the teacher's features. However, a low masking ratio in the teacher model means it covers more global information. This can lead to a mismatch with the student model's reconstruction task. We have noticed that the reconstruction loss rises when the masking ratio of the teacher model becomes quite low, which may support our conjecture about the conflict. Furthermore, we examined the average attention distance of DMAE, AMD and video MAE to reveal the properties of models. We find that at shallow layers, each model has diverse attention heads, which means model's attention is both local and global. While at deep layers, especially the last layer, most attention heads of AMD and video MAE tend to extract global informations, which is different from DMAE. In the video domain, the more global attention means that the model is able to capture more global information about the action, which is beneficial for action recognition. Therefore, AMD is better at tasks that require temporal understanding, which is due to the asymmetric masking strategy that allows the teacher model to see more contextual information. In this paper, we proposed an asymmetric masked distillation structure named AMD for pre-training relatively small models with auto-encoding. The asymmetric masking strategy allows the teacher model to capture more context information to transfer to the student model. We then proposed a serial feature alignment distillation method to take the advantage of the asymmetry, which leads to better exploiting of context information. In this way, we can train small and robust models with excellent generalization capabilities. The code and weights are available on GitHub. Please contact me if you have any questions.